Greetings A-level chemists, welcome to today's video on required practical 10 on the AQA specification, preparing an organic solid, but it applies to all of them, all of the exam boards, because chemistry is chemistry and it's not specific to just AQA, in my opinion. So, benzoic acid can be synthesized from ethyl benzoate. Okay, so we've got the reaction shown below and it's in alkali conditions. So what I might do is just draw the displayed formula for what's going on. So that's my phenyl group, so C6H5. So there's my C double bond O, and there is my C2H5. So there's my ethyl group that I've just drawn. So this is ethyl benzoate. So ethyl group and my benzoate part, which is derived from benzoic acid. And we're trying to make benzoic acid, so we're doing a base hydrolysis, and from the base hydrolysis we're going to react it with NaOH, and we will generate the sodium salt. So we'll generate sodium benzoate, and ethanol. Okay, cool. So we're following this prep, and the prep is given below. So it's added to a round bottom flask. Okay, and we've got a reflux condenser as well. So let's just talk a little bit about a reflux while we're here. Right, so we should have a reflux setup magically appear on the screen, and hey ho, we do. So let's talk about reflux for a second. So we've got our reaction mixture in the round bottomed flask. Could be a pear-shaped flask, who cares? So inside that we'd add a few of these little specks, and I know you're all thinking that these are anti-bumping granules. So obviously in a question, if they say what do anti-bumping granules do, you say that they stop bumping. That was a joke. No, you don't. We'll talk about what the role of the anti-bumping granules is in just a second. And then underneath this, we have a heat source. So it could be a heating mantle, or it could be a Bunsen burner. We're just going to draw it with an arrow. Okay, and then we have the condenser. So imagine this thing is being heated up, and we have a condenser attached to it. Notice that it should be open. So it has to be open. If it is closed, what's going to happen is the pressure is going to build up, and then boom, this is going to turn into a SUVAT question because you're going to have projectile motion. Okay, so then in this condenser, in the jacket of the condenser, what we're going to do is we're going to shade it in. So colouring in chemistry. So water is obviously blue, but that is too blue for my liking. So around the jacket of the condenser, that is going to be full of water. To make sure it is completely full of water, we have to make sure that the water inlet and outlet are in the right orientation. So the water inlet is through the bottom, so there's water in, and there's water out. So it's going in a counter current mechanism. So the reason for this is that all the condenser is full with water, so it allows for more efficient cooling. If we do it the opposite way and put water in through the top, we might get a region of space here where we don't have water. So if we have air is not a particularly good conductor, it's a very good insulator, so we're not going to get good cooling in that region. Okay, so that's the reason for it. So what happens is we start heating this up and the reaction mixture starts boiling. So to prevent large bubbles from forming and then boiling over through the top of the condenser, we use anti-bumping granules, and what these guys do is they provide a nucleation site for the bubbles. So smaller bubbles form. Rather than large ones. Okay, I think that's everything. Final thing is, so just remember the whole point of reflux is that we're going to get a vapor coming off of the reactant. So once the reactant vapor travels up, so imagine it's traveling up, what's going to happen is it's going to hit the wall of the cold surface of the condenser, and then it's hopefully going to condense, and the reactant mixture can then travel back down to the flask and then react with the other reactants. So it just means that we can continue reacting for higher yield, and so we don't boil dry. Okay, so that's the whole point of reflux. Okay, so a bit of a background. Now let's have a look at the question. So we've got to explain the use of anti-bumping granules, which we've done. I'm not going to go through that again. You can just see it from the previous slide. So using calculations, we've got to show that the sodium hydroxide is in excess. Okay, so it's 1:1. So let's first of all work out the mass of the ester. So let's have a look back. What is the mass of the ester? So I've got the ethyl benzoate, but I've got it as the density. So remember that the density is this symbol rho, which is the mass divided by the volume. So then to work out the mass, that's going to be the density multiplied by the volume. So I need to use this relationship here, okay? So the density of the solution, or the liquid, sorry, was 1.05 grams per centimeter cubed, and I use 5 centimeters cubed of it, so I get my mass is 5.25 grams of the ethyl benzoate. So then, to work out the number of moles of the ester, I'm going to take the mass that I've just worked out, which is 5.25, over the MR, which was given, which was 150, and that gives me the number of moles of 0.035 mole. Okay, and then to do the same thing for the number of moles of sodium hydroxide, and then we'll compare because it's 1:1. So what relationship am I going to use here? So this is going to be N equals C times V. So to work out the number of moles, that is going to be the concentration, which is 2 times the volume, which is 30 centimeters cubed, times 2. So N equals 0.06 moles. So the number of moles of NaOH is greater than the number of moles of the ester, and it's 1:1. And 1:1, therefore NaOH in excess. So that's the first part of the question. Let's continue. Okay, so some follow-up questions. Explain why an excess of sodium hydroxide is used in this reaction. Well, we don't have to overcomplicate this. Why do we use an excess of one reactant over the other? To make sure the reactant that is the limiting reactant fully reacts, so that all of the ester react. That's it. And then question 4, provide a reason why an electric heater is preferred over a Bunsen burner. So this is a safety issue, but we can't just say safety. We have to be a little bit more specific than that. So we can say that the alcohol or the ester are flammable, so therefore we don't want to use a naked flame. Right, that's it. Let's continue. Okay, question 5 of this question of RP10. So we've got to explain the purpose of using reflux in this hydrolysis reaction. Okay, so we spoke about this right at the beginning. To make sure that the reactant vapor, returns back to the flask to ensure they react. That's it. So then part 6, we've got to write the chemical equation for the reaction between sodium benzoate and HCl. Okay. So I'm just going to do it as displayed. I'm just going to put my carbons in here actually. So let's put my carbon in there. So here's my sodium benzoate, and if I add HCl, the driving force for this reaction is the formation of NaCl, and then we're gonna form my benzoic acid here. Sorted. Okay, so we've gone from the sodium salt to the acid by reacting or work up with an acid. Okay, question 7 of this question. Okay, so we need to provide an explanation as to why sodium benzoate is soluble in cold water, but benzoic acid is not. Okay, so sodium benzoate is ionic, so therefore soluble. But when we're looking at benzoic acid, so let's just draw the two out and compare and contrast. So if I dunk this into water, what's going to happen? That's going to separate. And because I've got a negative charge on that oxygen, this guy is going to be surrounded by water molecules. And so is the Na. Okay, so this is ionic, therefore soluble. General rule of thumb, ionic things tend to be soluble. Not all, there are exceptions, obviously. And benzoic acid is not. So let's have a look at benzoic acid. So when I'm looking at the benzoic acid, I've got this non-polar benzene ring. Non-polar benzene ring. Now you might be thinking, well, actually, look, you've got a carboxylic acid group there, and surely that can form hydrogen bonds with water. Yes, but then the non-polar benzene ring must be the dominating factor. So yes, this can form. So there's my lone pair. So yes, that can form hydrogen bonds with water. So we can get hydrogen bonding with water. So can form hydrogen bonds with water. Okay, but if we're going to structure our response, let's think about how we'll do this for 2 marks. So we've kind of got the 2 marks, we just need to put it in a more coherent way. So I'm going to say that the sodium benzoate is soluble as ionic, but benzoic acid is insoluble. Just going to say Ba for benzoic acid is insoluble, despite having, even though it can form hydrogen bonds with water through the COOH group, the benzene ring is non-polar. So there we go. Okay, last sub-question in preparing an organic solid required practical, and this is one that we should all be familiar with. Okay, so this is recrystallization. So we've made the solid benzoic acid and it's been separated by filtration. Describe the procedure that the student should follow to purify the benzoic acid. Okay, nice. Where do we go? So when we're recrystallizing, the first thing we need to do is dissolve the solid in a minimum amount of hot solvent. And then what we're going to do is we're going to hot filter this to remove any insoluble impurities. Sounds fancy, but it's not really, because all we're doing is we're filtering this, and then got a filter paper in here. We're filtering this when it's hot, and any insoluble impurities are going to be caught by the filter paper, and then our filtrate is going to be in here. Still going to be hot, presumably, okay? So then what we're going to do is we're going to cool it. So we're going to cool to recrystallize, okay? And let's think about this process. So if we zoom into this, gone from a conical flask to a beaker, but that's fine. So if we zoom into this, we've got a saturated solution, okay? Saturated solution of our benzoic acid. So let's say that's our benzoic acid. Obviously you can't see it, but I'm showing you that it's saturated. And it's still hot, that's why it's soluble. But remember, there might be some soluble impurities in here, but they're not saturated, okay? Because there's only a small number of impurities. So we've got a small number of impurities that are soluble and not saturated in the solution, okay? Because we're presuming it's relatively pure, just a few of them. If you've got a shed loads, then recrystallization is not going to be great here. You're going to think of another way. So then when we cool this to recrystallize, what's going to happen to my benzoic acid, which is a saturated solution at the moment? So when it starts to cool, well, this stuff's going to crash out of solution. And as it crashes out of solution, because it's less soluble as it gets colder, we're going to start to see crystals of benzoic acid forming. So these are my benzoic acid crystals. Okay, and what about my soluble impurities? Well, they're going to stay in solution because it's not a saturated solution, so there they are. So then to remove those, how are we going to remove those soluble impurities? Well, what we can do next is filter. So then we can filter under reduced pressure using a Buchner funnel and a conical flask with a sidearm, which is attached to a pump or a vacuum. So then once we filter under reduced pressure, what's going to happen is, here's my Buchner funnel. Not the best drawing. So that's sealed. Ooh, that one should be connected to a pump. So that's to the pump. And then once we add this, the soluble impurities, they're going to go through. I mean, there weren't that many, I'm exaggerating it. And then the crystals are going to be collected on the filter paper. Okay. And then we're going to wash to remove any soluble impurities. So once we've isolated our crystals, we'll wash it with some sort of solvent to remove any impurities that are soluble in that solvent, and then we'll dry the crystals. Okay, so there's recrystallization and everything you need to know about it with some fantastic drawings. Thanks for watching. Hope that was useful. Ta-ta.